Having learned what rational functions are, we're now going to learn how to simplify, multiply, and divide rational expressions. And then obviously we're going to take what we learned from there and transition it into learning how to solve rational equations. So for now, let's just talk about rational expressions. So we're just talking about one side of the equal sign that has that rational part to it. Of course, a rational is a fraction whose numerator and denominator can be written, are non-zero polynomials. Okay, now a non-zero polynomial also includes constants. So 5 over x plus 3 is also considered a rational expression because 5 is non-zero and x plus 3 is non-zero. Now, that of course depends on that domain that we're going to get into next. The domain of the function, it excludes values that make the denominator 0. Okay, which makes sense, right? So for example, that 5 over x plus 3 that I just mentioned, I think it was x plus 3. Well, we know that that denominator cannot equal 0 because you're not allowed to divide by 0. So I would have to say 5 over x plus 3, but we need to know that x cannot equal negative 3 because negative 3 plus 3 is equal to 0. Now we're going to start off talking about simplifying, and then we'll get into multiplying and dividing, because in order for you to multiply, you have to be able to simplify, and in order for you to divide, you also have to be able to simplify. So when it says get it into simplest form, the simplest form of a rational expression means that the numerator and denominator have no common factors except for, of course, positive or negative 1. Okay, so there's two skills that you really have to be pretty good at in order for you to successfully simplify, multiply, and divide rational expressions. And those skills are, number one, knowing your exponent rules. So for example, x cubed over x to the fourth. What happens to those exponents? So exponent rules, and then factoring. When we get into solving rational equations, you might have to factor 6 times in the same problem. Okay, so you really have to practice factoring. So if you know you're not there yet, you need to take out some time to practice factoring. So simplifying rational expressions, you've actually been doing this for a long time, right? Anytime you simplify a fraction, fractions are rational expressions. We've been doing that. So if I look right over here, it says a times c over b times c. I can divide those c's out, so I'm left with a over b. And that's how you simplify fractions as well. 15 can be rewritten as 3 times 5. 65 can be rewritten as 13 times 5. Those 5's divide out, therefore, you're left with 3 over 13. The same thing can be done with polynomial expressions of higher degree. So 4 times x plus 3 over x plus 3 times x plus 3. Those x plus 3's cancel, and so you're just left with 4 over x plus 3. There's just two main steps. The first step is you factor both the numerator and the denominator, and then you divide out those factors, just like in the core concept that we just reviewed. So let's put it into action. So example 1 says simplify x squared plus 7x over x squared. So remember, what I want to do is factor the numerator and the denominator and then see if any of those terms divide out. Well, I can see from x squared plus 7x, that's 2 terms. So the first thing I'm going to do, well, the first thing I would do anyway is look for a greatest common factor. And I notice that x squared and 7x both have a factor of x. So I'm going to factor out that x. which means I'm going to be left with x plus 7. Now, in the denominator, you might be thinking, well, that's just x squared. I can't factor that. Not really. However, you do know that x squared can be rewritten as x times x, right? And if you notice, at least one of those x's, well, not at least one, exactly one of those x's divide out, just like that. So that leaves me with x plus 7 over x. X plus 7 and x have no common denominators except for positive or negative 1, which means I am done. That one was a little bit more straightforward because all it was a GCF. Take a look at example 2. In the numerator, I have x squared minus 4x minus 12, which is a trinomial. And in the denominator, I have x squared minus 4. So again, I want to factor the numerator, factor the denominator, and see if I can divide out any terms. Now, luckily for us in that numerator, that a value is 1. And we love it when the a value is 1 because that means we don't have to worry about splitting up that middle term and finding those values that go into that table and then doing GCF again. It's a much shorter process because if I can find those two numbers, then I can go straight into my factors. Of course, if it is factorable. So I can go straight into my factors. X times x is what gets me x squared. Actually, let me put this into a different color. X times x is what gets me x squared. Now I'm looking for two numbers. When I multiply them, I get negative 12. When I add them, I get negative 4. So when I multiply them, I get negative 12. When I add them, I get negative 4. I'm going to have you pause and see if you can come with those two numbers on your own. Hopefully you get that those two numbers were positive 2 and negative 6. And in the denominator, you're like, oh my gosh, those don't have a GCF at all. I cannot factor that. I can't simplify. That's it. That's as far as I can go. But this is where I said it's really important for you to be able to factor well, okay? Because x squared minus 4 is actually the difference of perfect squares. X squared is a perfect square. 4 is a perfect square, which means I can rewrite this as x plus 2, x minus 2. And you're thinking, oh yeah, I forgot about that. Difference of perfect squares is so common, you guys. It shows up all the time. So notice now, x plus 2 divide out. So I am left with x minus 6 in the numerator, x minus 2 in the denominator. And I need to now think about that domain. So, of course, they both divide out and they're left with x minus 2, right? So my final answer, it's pretty obvious that 2 is not part of my domain. So I don't have to write that one down. What's not obvious, because it got canceled out, is that negative 2 is also not part of my domain, right? So let me clarify a little bit. Right over here, when I set that equal to 0, I get x is equal to negative 2. When I set that equal to 0, I get x is equal to positive 2. But if I never saw any of this at all, I only had my final answer, I would have no clue that that x plus 2 used to be in the denominator, right? And so I need to be abundantly clear, like, hey, this term is going to create a 0 in my denominator, right? So I need to say that there is a condition. X cannot equal negative 2. It also cannot equal positive 2, just to be clear. But that's still obvious from here. I can see that. I'm like, oh, duh, x can't be 2. I see it. But because those x plus 2's canceled out, they divided out. That's not obvious anymore. And so now I have to say x cannot equal negative 2 either. Okay? That's the same reason over here we didn't have to worry about it, because it's obvious x cannot equal 0, and same thing, even over here it was an x that got canceled, so that term is the same. Whereas over here, the term that divided out versus the term that's still there, they're different. So I have to be abundantly clear, like, hey, this term got canceled, and therefore that x value is not part of my domain. All right, on the next one, I'm going to go ahead and have you pause this video and attempt this problem on your own. All right, let's see how you did. Hopefully in the numerator, when you factored it, you got x plus 1, x minus 3. And in the denominator, you should have gotten x plus 2, x minus 3. So those x minus 3's divide out, which leaves me with x plus 1 over x plus 2. And I need to make it very clear that, hey, something got divided out, so I have to restrict my domain by something that's not visible. And that restriction is that x cannot equal 3. Because right here, when I set that term equal to 0, I will get a 3. So I have to make it clear. X cannot equal 3. It also cannot equal negative 2, but that's obvious from what I have left in my final answer. Okay? All right, now we're going to talk about multiplying. So if you're good at simplifying, if you did that problem pretty well, you're going to do great at multiplying. If you didn't do so hot on that example, then you need to go maybe do a couple more practice problems. There's tons in your textbook, there's tons online before you move on to multiplying. So if I take a look at this core concept, it says let A, B, C, and D be expressions where B cannot equal 0 and D cannot equal 0. So if I have A over B times C over D, that's the same thing as AC over BD. You know that. You learned how to do that with regular fractions, right? Now our job is going to have to be simplifying that AC over BD. But I learned how to simplify up in the previous section, right? Well, now it's just like simplifying a regular rational expression. So if I take a look at the example that I'm given, I've got this rational expression multiplied by this rational expression. Notice that we're just multiplying across, and then simplifying just like we did in the previous section. All right. Now, the first example I am going to break up like this just so you can see it a little bit clearer. But then from then on, we're going to go ahead and move forward like we normally would. So notice this is a monomial, 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 monomial. Okay, that are being divided. So I want to multiply across first. So I'm going to first do 8 times 7, which is 56. And then I have to do x to the 4th times x to the 4th. This is where I said your exponent rules are going to come in handy. I need to know, oh, when I'm multiplying terms with exponents, I add those exponents together. Then I'm going to do y times y cubed, which is y to the 4th, over 2 times 4, which is 8, x times, well, the other term does not have an x, so it's just x. Y squared times y is y to the 3rd. Now all I need to do is simplify that. And you've done this before. When we were doing exponent rules, you did problems just like this. You were simplifying rational expressions. So like I said, I am going to break it up a little bit longer just so you can see it. But moving forward, we won't be doing that any longer. So 56, I know, can be rewritten as 7 times 8. I also know that x to the 8th can be rewritten as x times x to the 7th. And you're like, Miss Johnny, why did you split it up like that? Why didn't you do x squared times x to the 6th? Why didn't you do x cubed times x to the 5th? Well, that's because I know that there's an x in the denominator that hopefully can be divided out, right? And like I said, you're not going to do it like this every single time. I'm just showing it to you that way. Also, I can split up a y into y times y cubed. Why did you do it like that? Well, because I know there's a y cubed in the denominator that's just waiting to get divided out. So now I'm going to move into my denominator. 8 times x times y to the 3rd. See why I did all of those on purpose? So those divide out, divide out, divide out, which means I am left with my final answer of 7x to the 7th y, and my denominator is done. Now remember, there's 3 things that got divided out in the denominator, right? And I no longer have any of those terms in the denominator. So I need to make it clear. X cannot equal 0 and y cannot equal 0. Because if they did, this would cause me to divide by 0, which I am not allowed to do. But in my final answer, I don't see that there used to be an x and a y in the denominator. So I have to be very clear about that. Now let's get into it where I'm actually doing a polynomial with several terms and I'm multiplying those pieces together. All right, now if you take a look at the back, this example for multiplication is different than the one that's on the front, because if you notice, our numerator and our denominator on most of these it's a polynomial, but it's got several terms as opposed to it being a monomial, which is just one term, right? Meaning several things multiplied. I've actually got addition signs and subtraction signs here. My recommendation to you would not be to multiply across and then try to factor, because those are going to get really long and a lot harder to factor. My recommendation to you would be to factor each of them individually and then see, okay, do I have any common factors that are going to divide out? So let's take a look at the first one. So I've got 3x minus 3x squared, and automatically I'm on like high alert because that is not in standard form. So I'm actually going to rewrite it in standard form first. So I'm going to say negative 3x squared plus 3x over x squared plus 4x minus 5 times x squared plus x minus 20 over 3x. So everything else was okay, but that numerator in the top left, that one was not in standard form, and I don't like that. So I'm going to first go rewrite it before I try to simplify. So now I am going to try to factor each of my numerators and denominators independently. So I'm working across because I don't know how much space I'm going to need. You are welcome to work your way down, okay? Whatever makes you more comfortable. So I have negative 3x squared plus 3x. Now, those look very similar, right? It's very clear that at least they have x's in commons and 3, but notice that the leading coefficient is a negative, and whenever the leading coefficient is negative, you always want to factor out a negative. So I have negative 3x, and that leaves me with negative 3x squared. When I factor out a negative 3x, that just leaves me with x. And then negative 3x, when I factor it out from a positive 3x, that leaves me with a negative 1. Now in the denominator, I've got a trinomial. So I'm going to see if I can factor that. Luckily for us, the a term is 1, which is awesome. We love that. X times x is x squared. And now I want to see, okay, are there two numbers that when I multiply them, I get negative 5, and when I add them, I get positive 4. So see if you can come up with those two numbers. Hopefully the two numbers that you got are positive 5 and negative 1. And you might be saying, oh my gosh, look, x minus 1, x minus 1. That's great, okay? But let's just keep going. Let's continue with the rest of our rational expression, and then we'll divide everything out at once, okay? So now let's move into our trinomial that's in the numerator of the second expression. Again, our a value is 1, which is awesome. X times x is x squared. And now I'm looking for two numbers that when I multiply them, I get negative 20. When I add them, I get positive 1. See if you can come up with those two numbers. Hopefully you got positive 5 and negative 4. And then in the denominator, of course, it's just 3x. Nothing to really do there. Now let's go ahead and start dividing out our terms. I've got x minus 1 over x minus 1. And I've got x plus 5 over x plus 5. Okay, which leaves me with negative 3x. Oops, I forgot one. I've also got a 3x and a 3x. Now you might be thinking, yeah, wait, that's a negative 3x. It is, but it's just like a negative 1 times 3x, right? So I still keep that negative, but the 3x's do divide out. So what I'm left with is that negative sign, and I'm left with x minus 4. Now, don't forget to restrict your domain depending on all of those terms that got divided out in the denominator. So when x plus 5 got divided out, which means x cannot equal -5. An x minus 1 got divided out, so that means x cannot equal 1. And a 3x got canceled out, so that means 3x is equal to 0, x cannot equal 0. Because when I divide both sides by 3, that leaves me with a 0. And so those are the restrictions on my domain as well as the simplified rational expression. All right, next one. Notice that this one also is a little bit different because I've got on the first term, I've got a rational expression and you're like, I can't do this. This is not a rational expression. Well, sure it is. All I have to do is create a denominator of 1. Okay, so we've got, I'm going to rewrite it first. We've got x plus 2 over x cubed minus 27 times x squared plus 3x plus 9 over 1. So now I'm going to try and factor each of those independently. Now, x plus 2 obviously cannot be simplified at all, so I'm going to leave x plus 2 alone. Now you might be thinking, oh my goodness, x cubed, I have no idea how to do that. Well, luckily, hopefully you remember x cubed is a perfect cube and 27 is also a perfect cube. This is the difference of perfect cubes. So this is actually going to simplify into x minus 3 because I keep the same sign, and then x squared plus 3x plus 9. Times. Now, you might be thinking like, hey, let me go try and factor that x squared plus 3x plus 9. First of all, it's not going to work. It's not factorable. But also, hopefully you notice, hey, x squared plus 3x plus 9. I'm just going to leave it alone. Over 1. Those two divide out, which means you are left with x plus 2 over x minus 3. Now, when you go to restrict your domain, you have to go figure out where does this term, or where does this polynomial equal 0? And what I would do is I would go graph it first, okay? So I have an idea of where it crosses the x-axis. And when you do go graph this trinomial, you'll see that it actually doesn't cross the x-axis at all. It's never going to equal 0, at least not any real number. So there is no value that I have to restrict the domain on here. Let's go ahead and write that as a note on the side. There are no real values for which x squared plus 3x plus 9 equals 0. Therefore, there is no restriction, or let's put no values need to be excluded from the domain. So because that polynomial is never going, because it actually ends up being a parabola, because that quadratic is never going to cross the x-axis, there's no times when it's going to equal to 0, which means there's no problems with any values in the domain. You can set this equal to, you can let the domain be all our real numbers. Now, if you recall from when you first learned how to divide fractions, when you have a fraction divided by a fraction, you actually multiply by the reciprocal of that second fraction. So A over B divided by C over D is this equal to A over B times D over C. And we just learned how to do multiplication, right? So it's kind of like we learned how to simplify, then we learned how to multiply, and now we're learning how to divide. But in order to divide, you have to be able to multiply. And in order to be able to multiply, you have to be able to simplify, right? So if you look at the example, it has 7 over x plus 1 divided by x plus 2 over 2x minus 3, which is the same thing as 7 over x plus 1 times 2x minus 3 over x plus 2. So let's take a look at this first example. It says, find the quotient of 7x over 2x minus 10 divided by x squared minus 6x over x squared minus 11x plus 30. The first thing I'm going to do is rewrite it as the product of the reciprocal of that second term. So 7x over 2x minus 10 times x squared minus 11x plus 30 over x squared minus 6x. At this point, it is exactly like the examples we did for multiplication. Exactly like it, okay? In fact, I'm going to ask you to pause this video and try to do it on your own. So let's start by factoring. Let's see if you got it right. So I've got 7x, which of course is going to stay the same. And then in the denominator, I have 2x minus 10. Well, I can factor out a 2, which leaves me with x minus 5 times. In my numerator, luckily for me, great, my a value is 1. So I can say x times x is x squared. Two numbers that multiply to give me 30, but add to give me negative 11. Those two numbers are negative 5 and negative 6. And in the denominator, my greatest common factor is just x, so x minus 6. Those divide out, yay. Those divide out, yay. And those divide out. I love simplifying rational expressions because it's just like divide, 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 divide. So much fun. It's so satisfying. So now all I'm left with is 7 over 2. Now, 7 over 2, like that's really straightforward, right? However, look at all of these terms that ended up having to cancel in order to create that 7 over 2. You've really got to be careful and restrict that domain. X cannot equal 0 because of this term right here. X cannot equal 5 because of this term right here. And x cannot equal 6 because of this term right over here. And there we go. Those are the values that are excluded from our domain. All right, let's do one final example. And this time you're going to have to factor something where the a value is not 1. I couldn't let you go without one of those. So it says find the quotient, 6x squared plus x minus 15 over 4x squared divided by 3x squared plus 5x. Again, I'm going to make sure that I have to create that denominator of 1. And now I'm going to rewrite it as the product of 6x squared plus x minus 15 divided by 4x squared times 1 over 3x squared plus 5x. Now, I have to go and factor each of those individually. Now, what I'm going to do is I'm going to come over to the side. I'm going to factor that 6x squared plus x minus 15. Okay, when our a value is not 1, it takes a little bit more work. I'm going to start by splitting up that middle term and bringing down that negative 15, bringing down that 6x squared. To figure out what goes in those blanks, I'm going to create a table, and I'm looking for two values, a times c, that add to b. A times c is negative 90. My b value is 1. So I'm looking for two numbers. When I multiply them, I get negative 90. When I add them, I get 1. So again, I want you to see if you can figure out what those values are. Hopefully you got that they are negative 9 times positive 10, because negative 9 plus 10 is 1. Check. So those are the values that I'm going to put into my blanks. So negative 9x plus 10x. Then I factor by grouping, so I'm going to do greatest common factor here, which is 3x. That leaves me with 2x minus 3. And greatest common factor here, which is positive 5. And again, 2x minus 3. Remember, the cool thing about factoring by grouping is you always know if you're on the right path, because what's in these parentheses will always be the same. So that leaves me with 2x minus 3 and 3x plus 5. So when I factor that numerator, that's what I'm left with. 2x minus 3 and 3x plus 5. I noticed that a lot of you guys, once you find these numbers, you go ahead and go to this step, but you can't do that without finding the GCF, okay? So like you'll make the mistake of saying, oh, that's going to be x minus 9 or something like that. You don't want to make that mistake, okay? So be really careful there. In the denominator, there's not much we can do. We're just going to leave it as 4x squared times 1 over, in the denominator, I can pull a GCF of x, 3x plus 5. Notice that these divide out. And that's actually all that divides out. So I am now left with 2x minus 3 over 4x squared. What happened to the 1? Well, when you multiply anything by 1, you're left with that value itself. Now we have to take care of that x as well, right? So let me scooch this over a little bit. 4x squared, and then I still have my times x in the denominator. Well, I can do 4x squared times x. That's just 2x minus 3 in the numerator, and then 4x cubed in the denominator. Obviously, x is not going to be allowed to equal 0, but again, that's obvious, right? What's not obvious is that x also cannot equal whatever causes this to be 0. If you can do that in your head, great. If you can't do that in your head, that's fine. Just come over to the side and say, all right, what value causes 3x plus 5 to equal 0? Subtract 5 from both sides. Divide by 3. So x cannot equal negative 5 over 3. So that's what I'm going to put right here. X cannot equal negative 5 over 3. Then equals here. And that is it. Okay, so get good at simplifying, then get good at multiplying. And if you're good at that, then you've got dividing. All it is multiplying by the reciprocal. All right, good luck. Do some practice problems. Get some help if you need it.